I'm going to talk to you about chapter 18, the Greek letters. First, see the example. As it is said, a bank has sold for $300,000 a European call option on 100,000 shares of a stock, and the price are as follow. The price is $49, striking price is $50, and so on. And then the black Scholes market value is 240,000. So as you can see, the difference of 300,000 and 240,000, which is $60,000 profit. So how does the bank make that amount of profit? So there are two ways. As you can see, they can do both by either naked position or covered position. The naked position, it just means taking no action at all, not doing anything and just leave as it is. Or you can do the cover position, which is like buy $100,000 shares today. However, they both have risks. For example, in the naked action, if you take an action, which I mean is like if you exercise the call option, you can lose the money. In cover position, however, if the stock price goes down, for example, assume that the stock price is at first $50 and then later if it becomes $40, the stock price value loses. And then there is also another strategy, which is stop loss strategy. It means, for example, buying 100,000 share dollars as soon as price reaches $50, or either selling 100,000 shares as soon as price falls below $50. So it just means reacting to the changes in price as soon as possible. And then, as you can see in the picture, between T1 and T2, as the T1 begins, you start to buy the stock because the price is above K, and then after that, between T2 and T3, you start to sell the price because it went below K, and then again between T3 and T4, you start to buy the price, and then so on. T4, T5, you sell it, and after T5, you just begin to buy the price again because it is above K. So I'm going to introduce you with the first term of the Greek letter, the delta, which just means that delta is the rate of change of the option price with respect to the underlying asset. So delta depends on two factors, which are option price and assets. And as you can see, the crossing point of A and B, and then the slope delta, which is the number, it is given as 0.6 in this graph. And also about the hedge, trade should be hedged with the position. For example, here it is short for 1,000 options and buy for 600 shares. And then there's one point that is like the gain is like the option position is related with the stock position. For example, for every gain on the option position, it is offset by the loss on the stock position, and likewise, the loss on the option position is also offset by gain on the stock position. Also, one point to remember here is delta changes as stock price changes and time passes. For example, it is given as an example on page 381 that, for example, if the delta price rises from 0.6 to 0.65, also you might have to change the number of shares, like from 0.6 to 0.65. There's a difference of 0.65. So you multiply it by the share amount. So you have to rebalance the hedge position. And then in delta hedging, it always involves maintaining a delta neutral portfolio, as I have mentioned before. And then there are two terms to remember, which is delta of a European call on a non-dividend paying stock, and it is termed as N of D1. And then the reverse of call, the delta of a European call on the stock, which is just N of D1 minus 1. These are just terms to remember. And then one thing to remember in delta hedging is there's a trading law known as buy high, sell low. And then there are two examples with two different scenarios. One is where the stock price on the first week it is just $49, and then the delta value is like 0.522. And then on the first week, if the stock price went down 48.12 in this case, the delta price also went down, and the share purchase, it is a negative number, so it means the shares are sold. And then as you see, as the as the share price decreases, the delta value also decreases. However, this is a second scenario, which is a different one, and then you can see the share prices are increasing 49.75, so the delta value also seems to increases to 0.568 and so on. Theta, another Greek letter, it is the rate of the change of the value with respect to the time. So theta is related with time. And one important point to remember is the value of theta for call and put is usually negative, which just means if time goes on, the value of long call or put option declines. So theta seems to be not very worth as you hold it for a very long moment. And then as you can see in the graph, the value is decreasing in a downward slope. And then gamma is the rate of change of delta with respect to the price of the underlying asset. And gamma is also greatest for options closest to the money. And however, gamma, as you can see in the graph, it is upward slope and then downward, going upward and then downward. And then there's a hedging errors caused by curvature here. What it means is like the value, the actual value seems to be at C double prime, C prime prime, but people mistaken it with C prime, so it is an important point to note. The call price seems to located at C double prime. And also to differentiate between the positive gamma and negative gamma, you can see positive gamma is in this shape and negative gamma is that shape. And this important point to note the relation between delta gamma and theta. So for a portfolio of derivatives, you have to know the differential equation of Black-Scholes-Martin, which just means as follows: theta plus r as delta plus half theta square equal to r gamma. And there's one more term known as factor, which is the rate of change of the value of derivatives portfolio with respect to volatility, and this is the graph of the Vega. And then in the expansion on chapter 18, you can see the Taylor expansions, which is another formula, which means value of a portfolio of derivatives is depend on asset price volatility and time t. So you can see it goes on like delta t gamma equal to delta into delta s plus figure into delta theta plus theta into delta t plus half gamma, and so on and so on. And also to manage these two Greek letters, these three, delta, gamma, and vega, to change the delta value, you can take a position in the asset, and then to adjust gamma and vega, you just need to take a position in option or other derivative. So asset is related with delta, and option is related with gamma and vega. Here you can see in the position. So here you can see the question is what position in option 1, option 2, and the asset will make these delta, gamma, and vega neutral. So we have to equal all the third row equal to 0 and the fourth row equal to 0, which is in gamma the portfolio value is minus 5,000 plus 0.5. We use W1 to find the unknown for option 1. 0.5 W1 plus 0.8 W2 equal to 0, and then minus 800 plus 2 W1 plus 1.8 1.2 W2 equal to 0. So there is two equations. So to find these two unknowns, we got 406,000. So we know from here, we know long positions of 406,000 in option 1 and 2. And then the last term, rho, which is the rate of change of the value of derivative with respect to the interest rate. So rho is a term that is related to the interest rate. And then these are the practical value of hedging. So they always have to ensure to check their portfolios that they are usually delta neutral. They always have to do that at least once a day. And then so they also have to check for the two Greek letters gamma and vega to improve to arise some opportunity. And also there exists economical scale, which just means as portfolio becomes larger, hedging becomes less expensive. So basically it means that if your portfolio, your investment is growing big, the hedging is not as expensive as the small portfolio. And also you can do a scenario analysis, which involves testing the effect on the value of different assumptions concerning by changing asset price and their volatilities. And then this is you can see in call option and put option for delta, gamma, theta, vega, and rho. You can see on Greek for European options on an asset that provide a yield at rate Q. So you have to use this formula to know it. And also future contract, they can be very useful for hedging. And then you can see that formula that the delta of a future contract on an asset paying a rate Q is e to the power r minus q time t, times the delta of a spot contract. And also the position required in futures for delta hedging, you can e to the power of negative r minus q times t times the position required in the corresponding spot contract. And also, there's a difference between hedging and creation of an option synthetically. So if we do the hedging, we have to take care of Greek letters delta, gamma, vega, and etc. to offset the position, and in option to create an option synthetically, we have to take positions that are in match with delta, gamma, and vega. And also, you can do the portfolio insurance. For example, in this case, in October of 1987, many managers attempted to put a put option, and this involves initially selling enough of the portfolio to match the delta of the put options. If the value of portfolio increases, delta of the put becomes less negative, and some original portfolio is repurchased. As the value decreases, delta of the put becomes more negative and more must be sold. However, the strategy did not work on October 19, 1987. What happened at that time is the Dow Jones stocks it's like they lost the value for about 20%, and then on October 16, the market declined by about 10%, and according to the portfolio trading rules, they should have generated at least 12 billion of equity. However, in fact, they can sell only 4 billion, and also it was estimated on Monday 19 that the sales amounted to 21.3% of all sales, and all. And also, it's like the decline in equity price was also made worse by investors because they are selling heavily because they anticipated the action of portfolio insurers, but this does not happen. So the strategy fails in this case. So sometimes the strategy cannot work very well. And that's it.
Okay, good. There is a good summary. Spot price, volatility, time to expiration. Okay. So derivative of S with respect to value, underlying the value is called delta. Okay. So delta means how much spot price change when how much value of stock change when the spot price change. Okay, slightly actually. So it's a derivative of, it is the value of taking differentiation of derivative with respect to underlying asset. Okay. And then vega, it is a Greek, delta is a Greek. And vega is actually not Greek. There is no Greek letter called vega. It is what will happen when you write the industry size notations. This is stupid notation. So anyway, It is the vega is what you get if you take derivative of the value of derivative with respect to volatility. And theta is again the ratio of the small change of derivative over small change of time dispersion. And gamma is also important. It is actually second derivative. Okay, delta is first derivative of stock price. No, first derivative of the derivative with respect to stock price, right? And then if we take derivative that one again with respect to stock price, we have gamma. Therefore gamma is second derivative. Gamma is therefore second derivative. Delta is first derivative. Right? Delta is first derivative, right? Where is it? Yeah, delta is first derivative, right? Round V over round S. And then gamma is round delta over round S. So it is round square V over round S square. And those four are important. Others are, I don't think they are important. Of course, we can calculate it. When the trading screen, we can observe those values, but they are not really used. Those four are important. Why they are important? It is important in order to do the hedging. Okay, so for example, let's go to slide. Okay, this one. Your portfolio, you have a portfolio which is delta neutral. Delta neutral means that delta is zero. But your portfolio gamma is minus 5,000, vega is minus 8,000. Right? Therefore, okay, if you go to this definition again, therefore, when volatility changes, when volatility of underlying changes, then it means you will lose $5,000, and you don't want that. Okay. When volatility changes, you lose $5,000, and there is clear risk, and you don't want that. And then when there is a change in gamma, it is second derivative. So it is not change of delta. Okay, so it is not exactly delta. So when underlying asset changes, of course your portfolio delta neutral, but the convexity is the convexity of your portfolio change, and that is also kind of like actually vega and gamma tend to move together. Okay, and again you don't want that. Okay. And the question is how we can make your portfolio not only delta neutral, but also gamma and vega neutral. That's your goal. Do you understand what this problem is? Okay. So basically those Greeks are at the sensitivity when value of some parameter changes. It is basically how much your portfolio value changes. Also gamma is second derivative. But again, it's change of change is changing. So it is therefore, when you think about risk is sensitivity. How much your portfolio value changes when some parameter value changes. Right? And you don't want that all to equal zero. But then your portfolio will be safe. Okay? You understand the question or the problem? Then suppose you have two instruments, option 1 and option 2. And then what you can do is you take some position of portfolio, some position of option 1, some position of option 2, and then you make delta neutral, gamma neutral, vega neutral. You take, so you combine those three assets together. So basically it is your own portfolio, but you can obvious portfolio also, and you basically add two more assets. Okay. You add two more assets, which is option 1 and option 2. And by adjusting portfolio across the three assets, you want to make all three zero. Then how can you do that? In the PPT slide, they show a method of doing this. And then actually this is not my preferred method. Okay. I prefer the method is suppose W0. Okay, W0. W0 is your weight on the portfolio. W1 is your weight on option 1, and W2 is your weight on option 2. Okay? Then those Greeks are all derivatives, right? They are taking differentiation, and derivatives are linear operators. Okay? If you take derivative of f, a fx, then it is, and if you take derivative, it is basically a multiplied by derivative of fx. So derivative is linear operator. So when you take position of W0, then your delta is 0 and your gamma is for your portfolio is W naught multiplied by 5,000. Okay, because derivative is linear operator. Okay. Then what? Delta, gamma, and then mega. Okay. If you take position of W0, then delta is neutral, so it is 0. Okay. And again, derivative is linear operator. So gamma of your portfolio is what? If we take position of W naught, then what is gamma of your portfolio? Usually, yeah, exactly. 0. And gamma is likewise, right? And then if we take W1 position of option 1, then you have, okay, right? And then you take W2, right? Something like this. And then basically in your portfolio you combine this and this. Okay. So your portfolio, in your portfolio you have W1 position of portfolios, W1 position of option, and W2 position of option. So therefore, okay. So your aggregate, your now new portfolio delta is what? And then your gamma is this one plus this one. And then your vega will be this one and this one, right? And then because in your aggregate portfolio you want to make them all 0, okay? So you want to make this one 0, this one 0, and this one 0, okay? And then you have 3 equations and 3 unknowns. I adjusting W0, W1, W2. I think you can solve this problem, right? Let's try. Okay, let's try. Okay, so 0 minus 8,000. Okay. Okay, so 이제 portfolio option 1 and option 2. Okay. So if you take position of 1, 1, 1, 1, then your delta is there any way to make this one smarter? Okay, so okay. Okay, so basically if you take position of 1, 1, 1, then delta, gamma, vega is not all 0. Okay, none of them is 0. So clearly it does not work. Delta, gamma, vega. So none of them is 0. None of them is 0. So what you have to do is you have to change the weight of this one. And then you want to make this one all 0. Okay? All 0. How can you do that? Then okay, so of course you can solve it by hand. Okay? And then if you don't want to use your hand, okay, then you can use W factor. And this one is symmetry. And then you want to make this one. Right? Eh? Yeah, that's one idea, but I'm thinking about even easier one than that. Okay. So this one. Oh. Wait. There is something wrong with this. One trivial solution is they are all 0. If they are all 0, then it does not make sense. 응? 뭐가 이상한데? 이렇게 하면 전부 다 0이 되면 이게 솔루션이면 전부 다 0이 돼야 되잖아. W0, 이런 말이 안 되고. 그렇지? 그러면 이걸 풀려면 슈퍼서 나오는 대로 풀어야 된다.
문제가 gamma 중립이랑 베가 중립을 찾으라고 했으니까 델타는 빼고 오른쪽 두 개만 가지고
아니 델타 중립도 해야 돼요. 이 PPT를 보면 결국 이 두 개를 풀어서 W가 400이고 6000일 때 400이고 6000이가 되고 이걸 3240을 해야 델타 뉴트럴까지 된다 이거지. 그러니까 이 두 개만 놓고 풀고 이게 0이니까 쇼컷으로 푼 거예요. 그래서 식은 자 3240 세 개 나간다면 3240 400 6000 이게 교과서에 나온 방법이죠. 이게 교과서에 나온 방법. 옵션 1은 그래서 400개, 옵션 2는 6000개. 물론 옵션 1은 이렇게 되고 책은 0 3240개 하고 품질을 취하면 죄송합니다. 네. 자, 이게 아니고 또 언더라잉 에셋이 있는 거지. 에셋. 네, 그렇지. 포트폴리오가 아니라 에셋. 죄송합니다. 그래서 이게 아니라 이 포트폴리오가 아니라 그렇지. 첫 번째 자산은 언더라잉 에셋이니까 1, 0, 1, 1. I'm sorry. So basically, what you have to do is you use 3 assets and then you want to make your portfolio working natural. So one other instrument is basically one underlying asset. If you have underlying asset and underlying asset is basically gamma, the underlying asset is just constant, right? It is just stock price, also stock. Therefore, is gamma and then vega is all zero. Okay. So by combining that, by combining your assets, something like this. Therefore, you want to make this one zero, and then your portfolio gamma is minus 5,000. Okay, minus 8,000. Okay, so first one is not portfolio, it is just the asset. This is option 1. This is option 2. Okay. Okay, sorry, I also made a mistake. So this is portfolio. And then you combining assets delta is 1, underlying asset is 1, and then gamma is 0, and then vega is 0, right? And then in the textbook, if we have a position of minus, okay, and then from product, okay, 0. So it exactly matches, right? So in your portfolio is delta neutral, gamma neutral, and vega neutral. So basically you want to combine 3 assets, optional and option 2 and underlying asset, and then delta, gamma, vega for those assets are given, right? And by combining those 3, basically you replicate portfolio basically. Okay. Right? Then it is there exactly the opposite. So if you add this one combination of option 1 400, option 2 6,000, 3 minus short position 3,240, then your hedging portfolio delta is 0, gamma is 5,000, vega is 8,000. So if you add them, they are 0. Right? Okay. So our goal is to calculating this one. Okay, this one. So you can combine this one as a matrix. So this one multiplied with this one. We want to make this one. So easy one is you. So basically your portfolio weight omega, and then matrix is green, and then you want to make this one as minus of the green. And then therefore your target portfolio, your portfolio weight would be this one is your Greek minus Greek multiplied by M inverse. Right. So M inverse is inverse Control Shift Enter. So it is inverse matrix. And in the inverse matrix, and then you multiply minus of this one and this one. Okay, so what you can do is now minus of M matrix multiplication, this one and then this one. Okay, then it is minus 400. Oh, okay, so okay, it is our portfolio, so not this one. Okay, sorry. So minus 3 minus multiplication of this one. Okay, your portfolio Greeks, and then inverse matrix of this one, and then your portfolio weight is 400 for option 1, 6,000 option 2, minus 3,240 for this one. Okay, for stock asset. So this is your optimal position. Okay, so now of course the textbook method seemingly reliable. I think this is more practical. This is more practical. Because you can solve this problem in one shot. In the textbook, you solve the problem in 2 steps. Meaning matching gamma and beta first and then match them. Okay. That's possible because of this one's gamma and beta is 0 and delta is 1. But if your third instrument is not like this, not under against it, it is another derivative. Okay, if it is another derivative, you have to solve the problem like this. So in this textbook method, the third instrument is basically asset, but it doesn't have to be. It can be another option. And you have to solve the problem like this way. Any question? So this is very important in your portfolio risk management. And another very important one in practice is called delta hedging. Okay. Okay, so let's go back to the problem. Okay, so suppose you are investment banker and then you have sold for 300,000 a European call option, 100,000 shares of a non-dividend paying option, and condition is like this, and threshold Merton value is 240,000. So basically, the worth of your product is 240,000, and you sold this one at 300,000. So you are good salesman. So you made 60,000 profit. Okay, that's good job. But problem is that that profit is not yet fixed. Okay, means that of course you sold it 60,000 higher. But problem is that it is still possible that you will lose money if option is exercised. So for example, strike price is 50. Strike price 50, and then if stock price becomes 51, okay, 51, then per option you have to pay $1, right? Because it's sold for, and then you sold 100,000 shares, right? Therefore, you will, if option or stock price becomes 51, and then option is definitely exercised, then you have to give how much? $100,000. Okay, you have to pay. Then, although you made profit of $60,000, it doesn't make sense. Okay, you will still lose money. Of course, if option is not exercised, if stock price is below K, okay, then your revenue is still 300,000. Right? If option is not exercised, 300,000. stock price option is exercised, you are likely to lose money. Okay? Of course, so on average, you occur all the possibility in the risk neutral way. Then your profit is 60,000, right? But again, it is not fixed, and therefore, question is how you can lock up that profit. That's a very, very important question. That's what investment. That's one of the business model of investment bank. Okay, they sold some product to client, and on the back end they have hedge out, so they actually have hard cash. Okay, otherwise they are exposed to risk. And then one, so suppose if delta, okay, if interest rate or volatility doesn't change, and if only underlying asset is likely to change, then it is enough to do delta hedging. Okay. And there is an example of delta hedging, I think. So in this case, first scenario, okay, if stock price is $49, and the delta of the call option looks like this. Okay, delta of European call option looks like this, ND1. So you calculate ND1. ND1, then delta is 0.5 to 2. So when stock price changes, something like this, okay, and again you can calculate ND1, and ND1 is also like this. So when stock price is very high, right? Stock price is very high, like $57 at the end, at the terminal period, then option is surely exercised, right? Because it is surely exercised. So whatever stock price change, that becomes valuable option. Therefore, delta is 1. Okay? It is natural. 무슨 말인지 알겠죠? This delta. So you have to have a delta hedging. You have a short position on the stock, short position on the call option, right? So you have to buy, okay? You sold the call option, short position of call option. So call option is basically when stock price goes up, you will lose money because you sold the call option. So intuitively, you purchase the stock, right? To hedge the position. So anyway, that's why you have to purchase delta multiplied by stock price. You have to buy delta amount of shares. Top call option. Okay. Top call option you have delta amount of shares. And then delta is 5.5 to 2, and stock price $49. And if you multiply this one, and then you have to purchase 52,200,000 because again, how many shares? Okay, so you need 100,000. Okay, option on 100,000 shares. So therefore, basically, what we have to do is we have to multiply this one and 100,000, and we have this one, right? Because per option, you have to buy this one, and you have 100,000 option, so you have to purchase this one. And then, of course, the cost is since you have to buy 52,200 stock, and per stock price is $49. Therefore, the cost is this one multiplied by this one. This is the cost, and cumulative cost is this one. Okay. So you have to pay this one, and you have stock. Okay. And then next week, for this week, from this one, because you bought this one, and you have to pay interest. There is approximate cost of holding stock, and this is interest rate. This one multiplied by cumulative cost multiplied by, I guess, what was the interest rate? The interest rate is 5%, and divided by 52, right? 52 weeks per year. Then it is a weekly interest. So your cumulative cost becomes this one plus this one. But in the next period, actually stock price went down. Stock price went down, so intuitively, option is less likely to exercise. So you can sell some stock, okay? Which means that now delta drops. Delta drops, so it means that you need stock of this one multiplied by this one multiplied by 1,000, which is smaller than this one. Therefore, you can sell this amount. So this one minus this one, this one minus this one plus this one is actually this one multiplied by this one, 100,000. Okay? Do you understand what I'm saying? So basically, you have to sell this one. So the cost. Okay. Now it is not cost because you sell, you make money. So you sell this one. So this one multiplied by this one is this one, $308. Okay. And so therefore, you have to add this one and this one and this one, and then you have this number. Okay. You understood that thing? Right? And then this is now your cumulative cost, the amount of stock you are holding, value of stock you are holding. There's another interest in this one. And the stock price goes on again, you can sell more, and you cumulative cost. You can keep doing this. At the end, your cumulative cost is $5,263,000. Right? $1,000. And then at this period, stock price is $57. And then since the strike price was $50, right? $50, therefore option is will be exercised. Option is will be exercised. Right? Therefore, what your value of your position would be this one, okay? This one plus actually you have to pay. Okay, stock price is, let me check, $50. So basically, you have to pay $7.25 per stock. Okay, per stock. Okay, and then therefore, if you add them together, then I guess in the textbook, let me see in the textbook 384 page. By week 20, therefore, the hedge has a fully covered position, so hedge will receive $5 million for the stock held. Okay, so that's the cost of rising the option, and the hedging is $263,000, right? Okay, because you have to receive $5 million for stock held, right? When you deliver stock, because the have option is right to sell, right to buy, some also as a strike price. So this is the value. Okay, this is the value. But when the option is exercised, you don't receive this amount, right? You receive it as $50. So $50 and 6,000. So this is 30. So basically you get 5. So the value of your position is $263,000 now, because this is your cumulative cost, and then you receive $5 million. Okay? So you get $263,000. Then that $263,000 is not exactly same, but similar to the threshold option price $240,000. Of course, there is small difference because you hedge only once a week, and if you hedge daily, then cumulative cost, your value of your position would be more similar to it. If you hedge continuously, then the value of your position will be exactly matched this amount. 이 질문이 있어요. 이거 굉장히 중요한데. 트레이더 때 여러분이 만약에 외환은행이든 외환은행이 아니구나 어디 가서 파생상품 트레이드 트레이더가 되면 맨날 하는 게 이런 거예요. 맨날 이런 거 하는 거예요. 별로 어렵지 않지, 그렇죠? 이 델타도 그 스크린에서 다 계산해 주니까, 그렇죠? 그 델타만큼만 사고 파면 되는 거예요. 진짜 쉽죠? 네. 델타를 곱한 만큼만 가지고 있어야 되고, 원래 가지고 있는 양이 얼마 살지만 알고, 그것만 사면 되는 거죠. 얼마나 쉬워요. 그거 하는 겁니다.
그러면
근데,
이게 주가가 매일매일 움직이잖아요.
네.
거기에 맞춰서 계속 그렇게 다 조정을 계속 매일매일 해주는 거죠.
자, 이제 자주 해주면 좋겠지. 그러면 더욱더 이렇게 가까워지겠죠. 그래서 6,000 프로핏 정확히 만들 수 있겠지. 여기 점점 마지막 포지션이 이거랑 점점 가까워지니까. 예. 근데 문제는 뭐냐면 자주 하면 할수록 또 트랜잭션 코스트가 스탁 트레이드하는데 공짜가 아니잖아. 비드 스프레드도 돼야 되고 커미션도 돼야 되고. 그러니까 또 너무 막 자주 할 수가 없다. 보통 하루에 한 번씩. 포지션 연착금은 좀 더 자주 할 수 있고. 이제 트레이더 능력이 헤딩을 하면서 얼마나 여기에 정확하게 맞추느냐. 언제는 좀 더 많이 하고 언제는 조금 저만하고 이렇게 하면서 스탁이 오를 것 같으면 좀 더 이렇게 풀었다가 했다가 스탁이 오르다가 해서 발로틀러티의 변화를 받아요. 이렇게 했다가 하면 돈을 버는 거지. 그래서 아무튼 6,000달러를 트레이더가 팔아와서 실제로 캐시가 되면 이제 이걸 판 세일즈하고 트레이더하고 그분 나눠받겠죠. 트레이더 보면 그래서 바로 성과가 나오겠지. 얼마나 헤딩을 잘했나. 이해가. So that's the one possible scenario, and second scenario is actually option is in this case not exercised. So again, the stock price $49, like this, and stock price went up. Stock price went up, so it means that option is now more likely to exercise. Option is more likely to exercise because if you delta increase, which is the increase, so you have buy more stock than before. How much? By basically this amount is this one minus this one multiplied by this one. You divide this one, and then cost is actually this one. So this one minus this one multiplied this one should be something. And it is the cost, and then cumulative cost of this one multiplied this one plus this one, this one plus this one plus this one plus this one. And you keep doing that, they will flow. And interestingly, at the end, the stock price is below the strike price, which is 50. Therefore, this option is not exercised, not likely to exercise. That has zero. Option is not likely to exercise, so this is the entire and this one, this you don't have to pay anything. Okay. And so this one is your final net position, and this one is again not exactly same, but similar to $240,000. This is option price. Actually, rigorously speaking, it is a future value, so you have to actually discount it back. You have to discount it back, and the match is $240, and that would be more similar. So anyway, 85 you can match this final amount into the $250,000 multiplied by 1 plus 5% over 5% multiplied 20 over 52 because it's future value, and you had a good job. You had a good job. 이거 굉장히 중요합니다. 얘는 어떻게 일하는지 알겠죠? 뭐 어떻게 하는지 알겠죠? 이거 기말고사에 내면 되겠지. 이런 문제. So one possible in-class final exam would be I give you some passive stock price and let you do delta hedging, and then you do delta hedging with your R formula and calculate the cumulative cost. That is one possible final exam. Again, let me announce your final exam again. The final exam would be you have two exam, two final exam. One final exam is take-home exam. Okay. one final exam is take-home exam, this one. Okay? I assume you are doing final exam very hard right now. This is one exam which is due 16. You have to submit this one by 16. Another in-class exam would be, your in-class exam is from June 20 to June 21. So I'll give today. If you come to class in the morning, then I'll let you know the outcome of the final exam, and then I'll give you 24 hours, and then after 24 hours, before you in class. If you don't answer the in-class exam, you have to do student project. Okay? You have option of doing student project instead of in-class. Eh? Student project. So if you write some sort of term paper, then you can skip in-class final exam, but you still have to take home final. But you should discuss the topic and method with me beforehand. One paper. 이런 게 훨씬 낫잖아. 뭐 외워서 시험 보고 싶어 솔직히. 그건 짜증나잖아. 이게 낫지. 근데 시험 공부할 필요가 없네.
만약에 두 번째를 선택하게 된다면 기존에 있었던 기말을 하고 이거 따로 두 가지.
아니 내가 말했잖아요. 그러니까 테이크홈 익점은 누구나 해야 되는 거고 이걸 하면 그렇죠? 이걸 하면 인클래스 익점을 없애줘. So again, this delta will be one part. This delta hedging is one possible incorrect coding. Another possible idea is I may assume not only delta but also vega change. So you have two. Okay. So you have two Greeks that keep changing. And you use two derivatives. So kind of version of this problem, dynamic version of this problem. Okay, you have to do this problem every day and match it. This is another possible incorrect take-home. Okay, so this is just one day, but every day this delta, this number in the matrix will change every day. Right? In that case, you have to do this on every day. That is not difficult, right? Yesterday you have a position of W0, W1, W2, and tomorrow you have desired position, and you can check by or only the difference between yesterday's position and today's position. And you can do it every day. That will be very practical in-class exam. So any question? Okay, why don't you take 15-minute break? Okay, let's continue the stochastic calculus. Let us assume the stock price S follows next geometric Brownian motion. Okay, so this is the geometric Brownian motion. It's like this. Okay. And then therefore thus I think how about ds square? Cool is such a 왜 안 보이지? 이게 메뉴가 안 보이네. 뭔가 이상한데. third equation. Okay. So what if ds follows that process? How about ds squared? What would be the process of ds squared? Okay, what would be the process of ds squared? Okay, yeah. If you multiply this one square and this dt square is 0 and dt is 0 and we have only dz square and dg square is dt. Right? So dx square is simply now. Alright. Sigma square s square and dt, right? Do you remember what you learned, right? Yes? You remember, everyone remember, right? 아, 그렇잖아요. 김효진한테 생각나니? 이렇게 되는 거 왜 그런지 이 결과를 기억하지 말고 please don't memorize the results. I explain the intuition of this. And there is a derivative of whose value is now fst. Okay. Suppose there is derivative whose value is like this. So s is clearly underlying asset, right? And from this one, by using Taylor series expansion, applying Taylor series expansion or what? E-theorem. I don't think you have to write down this one. I have shared this one, okay? Anyone with copy on and then fundamental PD, I'll share, okay? Link, insert link, okay? If you click this one, you reach this page, so you don't have to write down anything, okay? Then the process of the value of the derivative becomes what? Okay. Now df, what? df would be what first? ft okay, ft dt first, right? And then now x should change, right? X should change, therefore fx and dx, okay? Not dx, not ds, sorry. Okay. Okay. ds. Okay. So it is a high school. Up to now, it is high school math. So small change of f is determined by small change of t, because f is function of s and t. Small change of t and small change of f. This is high school math, right? So in the stochastic calculus, we have to take into account square 안 좋네. 이걸 한번 해보려고 했는데 F SS okay, and then 2 DS right, something like this. Okay, because now it is stochastic calculus. We have to think of, in addition to high school math, we can just add this term. And this term occurs because of the Taylor series expansion. 여기까지 쉽죠? 질문 없지? 유재민 학생 쉽지? 너무 그랬지 않아? 지금 어려운 거 조금 내가 어려운 게 있네. 어디? 뒤에 이 부분이 왜 이렇게 됐지? 네. So let's review Taylor series expansion. Okay. Taylor series expansion. Okay. Download. Okay, suppose we have a function fx. Taylor expansion represents your fx with some of the familiar terms such as x0, x1, x2, x3, something like that. Right? So the Taylor series expansion for fx around A looks like this. Okay? I explained why it should be look like this. It is in detail. Good news is that in finance, we do not have to think about term after x3. So x3, we can think of only this term. Okay. Therefore, we can write this way by slightly changing Taylor series expansion such that fx plus delta x equal, now x, instead of x we put x plus delta x, instead of a we put x, and equal fx plus fx delta x plus fxx x delta x squared, right? This is just Taylor series expansion. Okay, and by moving to this one over here, okay, and then if we add t term, if we add time, then ft plus delta t x plus delta x equal, this term is the same, and we own this one. Now change of the t time, okay, and then by moving this one over here, so change of fxx equal change of f from t plus dt to fx, which is just this term, this, right, this term, and then dfx, therefore d delta f equal ft delta t fx delta x plus 2 fxx over 2 delta x squared. This is exactly same to this term. Now you get, is everything clear? Okay. And then, right, from this one, if we plug this one, 뭐야 이게? 아, 이게 단축키가 안 되지. 네. This one, and put this one, and then f t plus, let me copy and paste this one. Let me copy and paste this one over 2. Okay, and then ds squared is also, I copy and paste maybe this one. Okay, dt. Okay, plus what? I have this term. Right? Any question? No, right? Because instead of dx squared, I copy it. Lori, you missed last week. So last week you were very good. 네, 여기까지 알겠습니다. Now, next, okay, next, let us consider the opportunity cost of buying holding, okay, holding the derivative, and okay, now if we have derivative of f, then what is opportunity of cost of the derivative of value f? We have to pay interest, right? And then every delta time t, we have to pay interest rate r multiplied by dt, right? Then we have to pay r dt, right? Per period, r interest rate, r per period, i.e. dt is our unit, right? Right? On the value f, right? Because value is the derivative price, right? Therefore, the opportunity financing cost for holding the derivative whose value is f is what? It should be what? Okay? If derivative value is f and every period you have to pay r multiplied by dt. So what would be your total finance cost? Okay? What would be your total finance cost? The value of f and per dollar you have to pay r multiplied by dt. So what? How much you have to pay? F multiplied by r dt, right? Right? It should be. Okay. Is naturally f r dt. Right?
exponential.
It is small period, so that's fine. It doesn't change it. Right? 그렇겠지. 이만큼 아까 델타 헤딩 할 때도 그 이자율 곱하기 이거만큼 계속 매기게 되잖아. 아니 익스포넨셜보다 이게 제대로 컨티뉴어스. 익스포넨셜 이거 익스포넨셜만 되는 게 아니라 정확히 이만큼 되는 거지. 이렇게 되는 아니 미분된 게 아니라 이 짧은 기간 동안에 정확히 RDT만큼 내는 거죠. 이렇게 되는 거잖아요. 그렇죠? 그렇지? Your net zero cost position is okay. So this is a derivative process, but in order to have this derivative position, you have to borrow money and invest it. Therefore, you have to minus RF dt, right? Okay? It is a zero cost because you borrow money and you invest every period. No 질문 있어요? Any question? No. And then okay. Your position is risky because of DS term, right? Remember, okay, time is deterministic. 1 minute later, We know what time is that time. Okay? And then all terms in the parentheses, okay, this is known, okay, we know F2, okay, so this term is all known, but this TS, only this term is not known because of this Brownian motion, right? So we know this term for sure, but we don't know this term. So our position is stochastic because of the DS term, okay? And we want to get rid of it. Okay? Hence, we want to remove the term. Okay, so in order to remove the term, we have to hold the underlying asset as by the amount of how much? How much you should hold? Okay. In order to get rid of this term, okay, this term, I want to have underlying asset appropriate amount, then we can get rid of this term. Okay. So how much? How much? 이제 마이너스 fx 아까는 델타 해칭하고 똑같은 거 아니야? 델타만큼 가지면 되는 거 아니야? So we have to do delta hedging, right? That's what we learn. By having the amount of delta, we can get rid of that term. Okay? F S i.e. delta hedging. So if we have delta hedging, we can get rid of the risk. Okay? And then of course, there is a financing cost of the holding stock as well, right? Yeah, for your and of course, you want to hold 칠판 안 쓰고 이거 하니까 훨씬 더 깔끔하고 보기 좋네. 그렇죠? Right? Okay. In the previous example, I only considered this term, but now I put the finance cost all together. Okay. If I have stock, top stock, then I have to pay RDD interest for every period, right? So this is the net position, and then I have delta, so I have FN. And then in order to have, I have a negative position, okay? I need a minus, right? V. Let's change V. Do you know what I'm doing now? This is another. This is also zero cost portfolio. Right? This is zero cost portfolio as well because I borrow money and invest in the stock. Actually, because I have negative sign, which means that I borrow stock and invest that money in the bank. And in the bank, they give me money RDD and period. Okay? So if we combine this and this, okay? This and this. Dynamics of now portfolio. Okay. Now I have to add what? Minus FS, but now I have a minus R S dt. Okay, so basically we have Okay, let me write down. Okay, this one, right? And then this equals, okay, and then this equals what? Okay, if we're combining the terms, then this cancels out, right? And this one moves to this one, right? So this one is what? Plus f f 네? 이 버그가 있어. 거의 이상해. 진짜 어이가 없네. fs and then rs something like this. Am I right? Am I right? I think I'm right, okay? It should be something like this. Okay? No risk and generate mystically per period, right? Right. Now no risk and for every period, my portfolio generates discount for sure every period. And I'm arguing that, okay, I'm arguing that, however, this term should be 0 because I'm arguing this should be 0. Why? This one should be 0. Why? Why is that? Can you tell me this one should be intuitively? We don't need mathematics here. Okay. 김효준, any idea why this one should be 0? Huh? No, that is the total volume. So, more intuitively, why? There's the right answer for total volume. I don't count total is the right answer. 김충현, why it should be 0? If it is not 0, what happens? 저 포지션을 만드는데 얼마 투자했어요? How much did you invest to generate this position? You invest this amount, right? So how much is that? How much is that? How much you actually invest to generate that position? Usually. It is 0, right? Because in order to invest derivative, you borrow money and invest, and in order to invest, you borrow money and invest stock. Okay, you source stock and invest money. So basically, you invest anything, borrow money and buy stock, or borrow stock or invest in bank, right? So you invest basically nothing, and you invest nothing and generate deterministic safe cash flow. It doesn't make sense. If this is positive, you can multiply large number over here and you can make infinite amount of money every period. If it is negative, you even you don't invest anything, again you can make infinite amount of money, right? Thing, okay? Release cash flow with zero cost. This violate no arbitrary condition. Right? So this should be zero. So we have very important one. So, therefore, so remember, f is a general form of the derivative. Right? F is very general. F is just arbitrary function of tau and time. So f is very general form of the derivative. Okay? Therefore, what? For any derivative f, the derivative should satisfy the partial, the PDE. satisfy what? T가 두 개네. Okay? Right? So f is general. F is just any derivative. F is by definition derivative. So it means that for any derivative, this will be satisfied. Right? For any derivative. Therefore, thus, if we solve PDE, this means if we solve PDE, we can get F. Right? For any partial derivative. So this is partial 평미분방 equation, partial differential equation. Because it has difference of t, difference of s. So it is called partial differential equation. So since any derivative should, the value of any derivative should satisfy this one, which means that if we can solve this one and get f, okay, then it will be the value of the derivative. Right? If we solve this one, we can get the value of derivative. Thus, we call the PDE as the fundamental partial. This is so important that we call it fundamental partial differential equation. Very important. It is fundamental partial differential equation because if we can solve this one, we can get any derivative. We can get the price of any derivative. Right? It is logical. It should be. Right? Logical. Then there is a small problem. Okay, call option, put option is function of time, and other I can say. But we know Black-Scholes formula for call option and put option is different, right? But we have only one equation. So how come? So basically, if we solve this one, I will show if we solve this one, we can get the Black-Scholes formula for ocean, American for American for everything, every ocean in the world. But thing is that all the ocean have different formula. How is that we have only one equation? How come we have all the different solution, all the option? Why? Eh? No, not at all. Why? Because the terminal condition is different. Valuation function of all derivative are the solution of the fundamental PDE with just different maturity condition. Okay. So for example, maturity condition F S T T. Okay. For example, if F S T equal max ST minus X0, what kind of option is this? This is called core option, right? Then the solution for the PDE is black choose core option formula. Okay? If then the solution is what? In this case, what is maturity condition for this one? What kind of if terminal condition is that one, what kind of contract is that? You have underlying asset and you pay X. What kind of contract is that? It is for the contract, right? For the contract with exercise with for the price X. Okay? It should be. Are you sure? Minus X. Okay, this is something you know, okay? We already learned. We will show that. We will do this perverted condition which is in the contract, okay, and then you solve this one here. Very easy, right? Of course, you already know even easier one than this is one. You can use binomial tree. You can use binomial tree in order to get any derivative price in the world already. This is number 2, second way of doing that. Actually, we have number 3, number 4 way. This second way, solving PDE. Actually, solving binomial tree, getting derivative with binomial tree is basically solving PDE. They are very, very similar to each other. And that should be similar because they give me the same answer, right? Okay, then the question is how to solve this one. Okay, how to solve this one? How to solve partial differential equation? Okay, that is another question. Could you please raise your hand if you take any class about partial differential equation? No? No, I guess not. How about ordinary differential equation? No? Never tried ordinary differential equation? That's fine. Okay. This is okay. Is not difficult to solve. The PDE is known as heat equation. Solutions are already well known. Okay? So this PDE is called heat equation, 열전도 강력해. So suppose there is a bar. If you put some light over here, then what is the temperature over some other side of bar? Then heat equation is solved. So if you want to solve this one, just bring this equation to your friends in engineering department, and they can solve it because they learn heat equation in engineering mathematics. That's number 1. Okay, all right. You can just apply heat equation, you can solve it. It's not difficult. Right? But how about if you are so lazy and that you don't want to learn heat equation, and maybe you are so hate mathematics, that you don't want to study heat equation, or you are so 왕따 or so social pariah, okay? You have no friend in engineering department, so that you don't have anyone to ask how to solve heat equation. Then what should we do? My argument is you can still be able to solve it. Okay? My argument is that, okay, moreover, in addition, you can solve the PDE even without solving heat equation. If you use economic intuition, okay, you can solve the PDE with high school mathematics. This is good news, right? So even if you don't have any friend in engineering department or mathematics, then even if you hate studying mathematics of heat equation, you can still be able to solve it. That's wonderful news, right? That's wonderful. If you know only high school mathematics. But instead of mathematics, you should have small economic intuition. Okay, so what kind of economic intuition we need? Let us take a hard look on the fundamental PDE and underlying asset process. Okay, let's take a hard look into the fundamental PD. This is fundamental PD. This is so important. It's fundamental partial differential and underlying equation. Okay, let's take a look at this one and then this one. Okay. Let's write down this one. Well, by the way, if you are interested in fundamental partial differential equation, if you Google it, then partial differential equation, no, fundamental solution, fundamental 블랙쉐드 데러거라 힐 이퀘이션. Here it is. Okay, this one. Black-Scholes equation. Okay, Black-Scholes equation. This is also called Black-Scholes equation. Okay, they are the same. Link, insert link. Okay, let's take a hard look. Okay, let's take a hard look at these two equations. Okay, this one, okay, this one and this one. If we take a look at this equation and this equation, in the second equation something is missing. What is missing? In the second equation, there is something in the first equation, there is something missing in the second equation. What is that something? G? Okay, that was hedged out. Okay, by taking delta, that is a good point first. Because I took delta hedging, I did a delta hedging, I removed the risk. And that's why in the beginning this should be 0 because there is no risk. Because delta hedging, I remove the risk. Okay. What else? First, we cannot see DG in the second PDE because we hedged out because of a delta hedging. Okay. Second, more importantly, cannot see what? That is not important. Okay. This is not important. Basically, this one multiplied by dt is 0, but dt is constant, so I remove. Okay. What is this like 소그림 자기? Mu, right? Mu. Right? mu does not matter. This means that when we evaluate derivative price, we do not need any information about the return of underlying asset in order to evaluate the derivative, in order to compute the derivative price of IBM. We do not need any information about what would be the price of IBM in future. Right? Because we don't need expected return price. We can just solve this one, we can get the derivative price. But thing is that in that equation there is no mu, which means that we don't need any information about price. When we calculate derivative price of quantum electron, we don't need any information about the target price or some future information or something like that. Nothing. But we already know this one because we already know this one from the binomial tree. In binomial tree, we have it the same. We don't need objective probability of going up, going down, right? We need only risk neutral probability. This is exactly identical to that distribution. Exactly same intuition. So they are now consistent with each other. Okay? So basically we can conjecture the solution of fundamental PDE from the insight that we do not need the information of the expected return of underlying asset. Right? This is our key insight. By looking at this one, oh, there is no mu. So now we can use high school mathematics. That's the conclusion. Okay. So how come? Okay. Okay. So since we do not need mu, we can replace it with any value we feel comfortable. For example, we can use what? 0 instead of mu. Okay? That's one possibility, right? Then it looks much simple. Then indeed there is a way. It is a fourth risk neutral measure. That is a solution for the fourth neutral measure. That's extremely easy. Right? Okay? That's the maybe easiest way. However, let us hold this section. Let us plug risk-free rate R into the place of mu. Okay? Then the process of underlying asset becomes now instead of this one is R. And in R, now we are thinking about different word. Okay, basically we are thinking about different word. So there is no this one head. I need head. Okay, let me use this one. Okay, something like this one. Okay. So I'm using this one head because it is like now we are in the different word. Okay. In the previous binomial tree we put star. Okay, let's put star. Okay, I think that's better. Right? 이 구글 닥에 뭔가 버그가 있어. 오케이. Okay. We put start because I put start in order to indicate that we are now assuming risk neutral word. Now we are assuming risk neutral word. Okay? It's like, as I said, it is like what? What is the Leonardo DiCaprio movie? The theme. What's Inception? It's like Inception, right? Inception, 팽이 있잖아, 토템. It's like a top. Okay? So we are in the different world. So in order to distinguish it, I put stop. It's like a top. Okay? Spin in the movie. It is risk neutral world because in the ordinary world, any risky asset, expected of any risky asset should not be risk-free rate. It should be higher than risk-free rate, right? But in the risk-neutral world, because everyone is risk-neutral, okay? All investors, okay? Investors make decisions only upon expected return, right? Not risk, right? Because there are risk when we make investment, we actually risk and return, right? With the risk and return, right? But in the risk neutral world, they don't care risk. They only look at return. So when return is slightly high, everyone wants to invest that stock. When return is slightly low, then everyone will short sell stock. So which means that everyone then every expected return therefore should be equal, right? Slightly high, everyone invests there. Slightly low, everyone short there. Every return should be exactly same. In addition, but then question is in what level everyone should be same? In the risk neutral rate, risk free rate. At least we know what is risk free rate, right? We means that everyone should every return equal, especially to R, right? That's our intuition, right? It means that every return should be expected return, right? Any question? It is a logical conclusion, right? It is a logical conclusion. It means that this means that the expected price of any asset at time t should be 잘못 눌렀네. equal 2 okay, expectation of this is actually what you already know. Okay, this is actually what you learned already. 아, 이 단축형이다. 단축형. 단축형. Right? It should be, right? Because every return generates exactly same expected return. Okay? So at time t on asset, okay, expected price of any asset. Let's say V is on asset price. So price of asset at time t, no, price of asset is V, and the price of it at small t, we know this, we can observe this one. Suppose you are at time t. Should be exactly the same to at t times rate, delta t times expected price discounted. Okay. So if you invest small v small t in the bank, then at time t your money becomes this one. If you invest this money in this asset, the money becomes this one. Because every expected return should be same, they should be same to each other, right? 중요하네. 이해가 가요. 그렇잖아. 사이에 more concretely, let's divide each side with VT. Okay? Then this is return from bank. This is return from derivative. Return from an asset. Right? 그렇잖아. Or actually not addition to this one. If there is a dividend, you should okay. If there is a dividend, okay. If there is dividend, we have to subtract by the amount of Q, okay. Because if you invest in this asset, okay. So if you hold this one, okay. Hold this one, then this one will generate Q every time. So the capital gain, which is ratio between this one and this one, should be less than the dividend rate. Because if we include that dividend rate, then the sum of the dividend rate plus capital gain becomes exactly risk-free rate, right? Therefore, the capital gain between this one and this one should be R minus Q, T minus T, right? That's fair. In that way, if become capital gain plus expected capital gain plus dividend become exactly risk-free rate. Remember, we are in the risk-neutral world, and every asset should generate exactly the same return, which is risk-free rate. Right? So this also applies to any derivative. Thus, the price of derivative copy or paste, okay, for any asset. Any asset. Derivative. So if we move this one over here, then this is minus. This is minus, right? And this holds for any asset. Derivative is also asset, right? Therefore, instead of this one, I can simply add can I recycle? 써주자. Okay. T should be equal to okay, right? It should be right. Any derivative price should look like this because derivative is also a set. And then because this is the derivative price, so this means that this should be the solution for the fundamental PDE. Okay. Indeed, this is solution for heat equation. Okay? So this is the solution. Okay? Okay? For example, instead of this one, if you put max s minus x 0, then this one, if we solve expectation and discount it, it is a Black-Scholes formula. Okay? Instead of this one, if we put over there bf minus x, no, st minus x, then it becomes value of the Ford contract. Right? And actually I will show you that this is high school math. This is high school math. Do you know what I'm doing? So from delta G, from stochastic delta, we derive the fundamental PD. Fundamental PD should be 0 because if otherwise there is this violate arbitrary condition. And if it is 0, it should be 0, which means that any derivative should satisfy the fundamental PD, which means that if we solve that fundamental PD, we can get any price of the derivative. By the way, in fundamental PD, there is no expected return term. It means that we can use any return for expected return. And what if we calculate expected return? Oh, then it means that it doesn't matter. So it means that we can regard underlying asset follows risk neutral dynamics, which means that we are in the risk neutral world, which means that we can solve the PD in the risk neutral world. But in the risk neutral world, it is trivial. Any asset price is trivially determined by this one because expected return should be risk free. Therefore, derivative price should be like this. And indeed, our conjecture is right. If we plug this one to our fundamental PD, it becomes exact 0. And this is our solution. Isn't it beautiful? This is very beautiful, right? So, you don't need heat equation. You don't need engineering department friend. You just need a high school first check, high school math. You can get Black-Scholes formula. Okay? See the following. I'm not sure we have enough time, but let's do it. Do you have class 있던 다음 시간에 12시부터 수업 있는 사람? 없지? 네, 이것까지 하고 가죠 오늘. 하는 김에. Okay, follow link. Let's click. Then I kindly drive the equation for you. Okay? I think I'm too kind. Okay. Again, for simplicity, we assume the asset price follows a geometric Brownian motion like this. Okay. Under risk neutral measure, it follows this one. And to apply it to formula, we have this equation, right? This is what Hyojun and what you did last week, right? So this one because this one, right? So this one risk neutral measure, this one. Okay? Integrating this stochastic differential equation. So from this one, it is between time 0 and t. So from this one, we have this one, right? Now we have this term, right? Up to now, you don't have any question, okay? Right? dst d log s is in this case log st minus log s0. We are integrated from time 0 to t, so it's log t over s, right? And dt is basically dt is therefore t, right? And dz is gt minus g0, so which is epsilon root t. Okay, so we have this one. Okay. So from this one, by using this one, we have this equation. Then we suppose let's assume there is no division. Okay. There is no division. And the risk neutral value, we know that this should be the solution of fundamental PD, right? Price of call option at time 0 is discount of terminal period, terminal price. And terminal price is call option price is discount of max ST minus X, right? This is what I just showed. 그렇지? 유재민 학생 질문 있나? 하나도 안 어렵지? 하나도 안 어려운 게 없어, 진짜. Nothing difficult. I guarantee no one can teach you this one easier than I do. I'm pretty sure. 김효진 학생 어렵나? 하나도 안 어렵잖아. 김효진 학생 어려워 보여. 내가 그랬잖아, 고등학교 수학으로 탈 수 있다고 한 거잖아. So let's solve this one. Okay? Okay. So using risk neutral measure, we have so instead of ST, okay, I plug just this one. Okay. So instead of this one, I plug this one. So in order to calculate expectation, this one, okay, ERT is over. By the definition of integration, by the definition of expectation, I do the integration from minus infinity to the plus infinity. And instead of ST, I plug this one S0 E R minus sigma square over 2 T sigma epsilon root T minus X. This plus is this shorthand notation of max this one plus 0. Okay? Instead of max this one plus 0 is too long, so plus. Which means that if this is positive, that term survives. If this is negative, it is 0. Okay? And then it is epsilon is standard normal distribution, and this is standard normal probability density function, 확률 밀도함수. So high school math. Expectation is integration, just multiply 확률 밀도함수, probability density function, and do the integration from minus infinity to plus infinity, right? So let's do this one, okay? But I want to get rid of this weird plus term. So I want to find the exact interval in which this one is positive, interval is negative. If then I can get rid of this one, right? So what my plan is, I want to get rid of this one, and then instead I change the integration interval. Okay? So let us see for the price formula without dividends, and let's denote f looks like this. Okay? And then in order to find the integration interval, so let me find the point of epsilon in which this one is 0. So to find this one is 0, okay, so this one, and I plug this f over here. then it becomes f e minus e sigma square t over 2 plus sigma epsilon root t minus it. And I want to find the point of epsilon, then make this one 0. Okay, and it's easy to solve. Okay, I take log each side, and this one, then epsilon is 0. Therefore, the solution when epsilon is d2, okay, when I move this one over this one, so when epsilon is this point, okay, when epsilon is d2, okay, then this one is 0. Therefore, if I plug this one d2 instead of epsilon, so epsilon is greater than d2, this one option is exercised. Epsilon is less than d2, then option is not exercised. The option becomes 0 as terminal period. So therefore, I can get rid of this weird plus 1. Okay. Instead, I just integrate from minus d to infinity, and other thing is the same. So instead of plus, I put minus d2. Okay. Because if epsilon is d greater than d2, option is exercised. Okay. And then, because we have this one, let's do the integration piece by piece. This one first, and this one later. Okay? So first part. For the first part, let's ignore this one, e minus rtt. So let's integrate only this part. So f is constant, so put f outside. So f minus d2 to infinity. E minus sigma square t, so this term survives, and I have to multiply probably the density function. Oh, no, but there are two exponential, so I combine these two exponential, and it becomes f minus d2 plus epsilon plus infinity, and this one. And this one is interestingly a plus b square term. Looks like a plus b square. So this one can be simplified this one. Okay, this one. Then this is the, okay, then interestingly, this one is probability density function in which mean is sigma root t and variance is 1, right? Right? When n mu sigma square, probability density function is right? Something like this, okay? So sigma square is 1. Instead of mu, I have sigma root t, right? So it is basically probability density function in which mean is sigma root t and variance is 1. So basically this one means this one means mean is what? Mean is sigma root t, and I want to do integration from d2 minus d2, right? And I want to get this area, right? And then idea is that, okay, let's shift this one to 0. Okay, parallel shift of this entire graph. If we do the parallel shift of this entire graph, then this area is basically, okay, now to make center 0, and basically this one is now minus d2 minus sigma root t, right? Right? Okay, it should be. Okay, so I'm just parallel shift the area of this one and this one thing. And then they are symmetric each side. So I flip, okay, in the size of this area, is therefore, if I flip this one, if I flip this one, this is sigma root t d2, and this area, right? And the size of this area is simply n d1. d1 is, I just define d1 as a d2 plus sigma root t. Okay? Right? This is the cumulative density formula. So this area is n d1. d1 is d2. Let me call this one as d1. Okay? So d1. So basically, if I include this one, the first term is n d1. Okay, d1 is d2 plus d2. Now let's investigate second term. The second term is now even easier. X minus d2 infinity root t. So it is just standard density function. Okay, so this is okay. This is same probability density function, mean 0, variance 1. So it is from minus d2 to the infinity. So size of this area, right? Size of this area. So again, if we flip, it is size of less than d2. Oops. 0. Size of the d2. So this size, so it is n d2. Right? This size is n d2. Right? N is again cumulative density function. So this is x n d2. As a result, so solution is, if we include the beginning e this term, then e r t f n d1 x n d2, which is exactly same to Black-Scholes formula that I taught you. So I told you it is high school mathematics, but it is even easier than high school mathematics. Right? I basically didn't do much integration. I just draw couple of figures, and that's all. It's such a simple, right? So I drive right? So you don't have to solve huge equation, just little economic intuition about fundamental parts of the economic situation, then you can solve Black-Scholes formula. Easier than high school math. I think this is enough for today. Any question? This is too easy, right? It's very beautiful and easy. NASCAM is extremely beautiful. It deserves Nobel Economic Prize. They got Nobel Economic Prize not because they solved this high school mathematics. No. They didn't get Nobel. It is high school mathematics. How we can give someone Nobel Economic Prize by solving high school mathematics? Does not matter. They got Nobel Economic Prize because they showed that we can derive these formulas with high school mathematics equation. Such a simple, easy way. Okay, let's see you next week. Who do the presentation next week? Okay, see you next week.